This is level 1 of the CFA program, the topic on quantitative methods, and the reading on sampling and estimation. Allow me to begin this recording with a quick example. Let's suppose that you and I are super interested in dividends. And in particular, we want to study the dividend yields of the 6,000 or so firms that trade on the NASDAQ and the New York Stock Exchanges. Notice that first part of the title of this reading, sampling. Well, we could go out and collect data on all 6,000 of those firms. Maybe that data is available, maybe it's not. But what we're likely to do is to probably reduce our costs and try to improve efficiency. Let's just take a sample of those 6,000 firms. Maybe our sample size will be 50, maybe it'll be 100, maybe it'll be 1,000. But what we're going to do is take that sample and probably try to extract some important characteristics about that sample so that we can make general conclusions about the population. For example, we're probably interested in the mean dividend yield and probably the standard deviation of the dividend yield. And so what we're going to do, the second part of that title, estimation, we're going to use that stuff from the sample to estimate and make conclusions regarding the entire population of dividend yields. Now, the one thing that we're going to know is that we're going to make that estimation with some kind of an error. So really what we're doing in this reading is trying to be able to use some tools to make conclusions about a population of data, like dividend yields, like operating cash flows, like composition of boards of directors. Now you'll see that going through these learning outcome statements that there are terms in there that we've seen in some previous readings. Probabilities, we did that. Errors. Now we haven't done simple or stratified or cluster sampling, so that's a new one, that third one. But we've talked about central limit theorem, we've talked about standard errors, we've talked about estimators and confidence intervals. I will introduce this concept of bootstrapping and jackknifing. These are going to be important concepts when we get into level 2. So it's important that we understand that here early in level 1. And then a final learning outcome statement asks us to look at ourselves and look at the surrounding area and say, okay, we've done this sample. Are there any kind of biases in there? And those are really, really good potential exam questions. All right, so let's go ahead and start off with the difference between probability sampling and non-probability sampling. And based on our discussions from the previous readings, you ought to be able to figure out what the difference between these two are. Look at that first diamond point under probability sampling. Each member of the population has an equal chance of being selected inside of a sample. So we can do that at least two ways that we'll talk about here in this reading: simple random sampling and stratified random sampling. And there's a good example. If we have a list of 500 hedge funds and we want to take a sample of 50, what we could probably do is some kind of a random number generator. Think of an Excel spreadsheet where you put these 500 somewhere and you assign numbers, and then you hit your random number generator function to get those 50 hedge funds. So equal chance of being selected. Non-probability sampling, on the other hand, has a lot to do with the researcher and how he or she views the population and or the sample. So there's one called a convenient sampling and there's one called a judgmental sampling. We'll talk about that in just a few minutes. Let's go ahead and get some definitions out of the way. Sampling error, difference between the observed value of a statistic and the quantity it is intended to estimate. So let's go back to my example with the dividend yields. Let's suppose that the population dividend yield is 5%. And we pick a sample of, let's say, 30 firms that are the largest firms traded on either of those two exchanges. And the average dividend yield, for some crazy reason, turns out to be 5%. Well, then the sampling error would be 0. So notice what we have written as the example. Any difference between the sample mean and the population mean. And of course, this can be caused by a number of reasons, but the primary reason is through what's known as the sampling error. The selection of the sample is not representative of the population of a whole. So let me take a crazy example. We have these 6,000 firms. Some of those are going to have dividend yields of 0. So let's suppose that in our selection of a sample that we pick 30 firms that don't pay a dividend. So you get their mean dividend yield, it's going to be 0, right? But you erred in selecting your sample because it wasn't really representative, right? Non-dividend paying firms are not really representative of dividend paying firms. And then in some qualitative research, there are ways to incur non-sampling errors that have lots to do with formations of surveys and questions during interviews. Look what we have written down there on the bottom line. The sample must be drawn randomly and encompass the whole population. Remember that we would love to have population data, but the population data might be, might be too big, right? We can't carry it on our shoulders. Or, and this is probably a more likely outcome, that it's way too expensive to find out and to collect all of the population data. So what we try to do, right, marginal cost, marginal benefits. So that's why we put together this whole sampling process. All right, let's look at the difference between simple and stratified sampling. Simple is exactly what you would think that it would mean, that there's an equal probability of being picked, and it's just selecting a sample from an entire population. So it doesn't favor one set of the population, and it doesn't exclude another set of the population. But what if we go back to my dividend yield example, and we ask ourselves the question, hey, what happens if there are interesting characteristics about the firms that pay dividends? Maybe there are interesting characteristics about the industries of those firms that pay dividends. So notice what we have in that gray box. Glaring differences within the population. Unreliable, simple sample inferences. So we stratify, and so all we do is we divide it here and here and here and here. And so look at that last circle point. Each stratum is composed of elements that have a common characteristic. And so here's a good example. So suppose we have 1,000 stocks. Some are small, some are mid, some are large cap stocks. So you have 1,000, right? But then you have these different categories or stratums, and you just simply divide those. And so let's go back up to the very top. Once the population has been subdivided, a simple random sample is taken from each stratum, and it's combined to form an overall final sample. And so what that's going to do is that's going to be representative of the population. And that should make perfect sense. Now back here, let me go back here real quick. Here we kind of were aware of some of those differences, right? Small, mid, and large cap. That makes sense. But let's suppose that we're kind of maybe unaware of some of those differences, yet those differences, those underlying differences might influence our sampling process. So to handle that, we can do what's known as cluster sampling. And there are a variety of ways of doing this, but look at the picture there. We could just draw a picture and plot all these variables on some type of a graph. Some are more complex than others, obviously. But notice that we call this good clustering. And let's go back to my dividend yield example. Something that maybe we wouldn't think of, but maybe we'd find out if we do some clustering. How about this? How about the age of the boards of directors that are declaring these dividends? So maybe there is a subsample, maybe there's a cluster of boards that have relatively younger board members, and when those board members sit around talking about dividends, they say something like, oh, you know what, let's reinvest all of those cash flows into positive net present value projects, which will allow us to pay dividends, higher dividends at some time in the future. On the other hand, maybe you have a population of board members that are in their 50s or 60s, and these smart men and women say, well, we want to pay a dividend to our shareholders because they need it as income. So it's really just one of those differences of willingness to take risk. In general, younger people are more willing to take risk than people in their 50s or 60s. So maybe the clustering here, and we can do this in 1 stage or 2 stage, maybe that cluster can identify those important variables. And then, of course, those clusters are also useful, even if it doesn't identify those individual elements. But clearly, if there is clustering, then we need to make sure that we include all of the clustering in the sampling. Yeah, I told you we'd get back to these non-probability sampling. So convenient sampling. Members in the sample are selected because of their convenient accessibility and proximity to the researcher. So this is the path of least resistance. Let me tell you a quick story. When I was in graduate school working on my dissertation and then trying to publish some other papers, I was doing research on Dutch auction repurchases. And back in those days, the only available data set or information set came from what was known as the Wall Street Journal Index. It was this big old thick book. And I would spend tons and tons of hours in the library looking inside of this annual Wall Street Journal Index to find firms, to identify firms that used a Dutch auction repurchase. Hours and hours down there. I would prefer to call that inconvenient sampling because it wasn't easy to do for me. But you can get the sense here. Convenience, if it's right here, then I'm going to use that sample. Judgmental sampling, this is even more interesting because this is based on what you would think is the researcher's knowledge and professional judgment, so that the researcher says something like, okay, going back to your example, Jim, with the dividends, well, I know that these 100 firms, they better represent the entire population than all these others based on my knowledge and professional judgment. Now, of course, when you have this judgmental sampling, you're going to be subject to some bias. And that's really why the Institute puts that last learning outcome statement in this reading. And we'll go ahead and look at that at the very end. All right, here's an LOS that we've seen before. Explains central limit theorem and its importance. We did this just in a previous reading. And remember, central limit theorem tells us lots and lots of stuff about a sample. And you remember I gave you a couple of guys' names, Chebyshev and Lyapunov, and these guys lived a long, long time ago. And they were studying statistics, and they said, all right, we can take a sample. But then let's suppose that we take other samples. Suppose the population is this big. How many firms pay a dividend out of those 6,000 on the NASDAQ and the New York Stock Exchange? I don't know, maybe 4,500, let's say. So, we take a sample here of 100 and a sample here of 100 and a sample here of 100. Well, this central limit theorem tells us that if you take all these samples and then you take the mean of all of those samples and then the standard deviations and the variances, well, you get a picture that shows down there on the bottom right of this slide deck. So let me go ahead and read that box just to make sure you understand this from a statistical standpoint. Simple random samples, each from size n from a population with a mean and a variance. The sample mean x approximately has a normal distribution. So each of those samples, if you do enough of them, right, they're going to look like a normal distribution. And so look at the circle point. This is a very useful tool. Of course, it's a very useful tool. And then we can go look a little bit more specifically at this illustration. And you should remember this from the very last recording that I made. 68%, 95%, and 99%. That's 1 and 2 and 3 standard deviations away from the mean. And so the really cool thing about this is we're going to use the basis of this central limit theorem to do things like confidence intervals. But before we head on to confidence intervals, let's go ahead and talk about the standard error of the sample mean. That's the standard deviation of all of the sample means. And what it does is it gives us an estimate of variability. And look at that second half-blocked point there. While the standard deviation measures the variability obtained within one sample, the standard error gives the estimate of the variability between all of those samples. So that's a really, really super definition and distinction that you need to make. Remember the difference between standard deviation and standard error. If I were creating exams, I would absolutely ask that question. So then the question becomes part of that LOS, calculate, right? So we need to calculate it. So there's a good old formula there. If we know the population standard deviation, then we just divide by the square root of n. Now, why is this so important? It gives the analyst an idea of how precisely the sample mean estimates the population mean. You know, for example, going back to my dividend yield, suppose that population mean is 5%, and our sample mean, we do a sample over here and a sample over here and a sample over here. The means are 10% and 20% and 30%. Boy, we have to scratch our heads and say, all right, we did something wrong, but that something wrong is going to be formalized in this standard error. So look at the second arrow point. A lower value indicates more precision. A larger value indicates less precision. And then there's a simple example at the bottom of the page where we just take our population standard deviation. So it's known. Remember, that's got to be known. 3 divided by the square root of 30 gives us 55 cents. All right, let's bury ourselves back into undergraduate statistics class about an estimator. So this is a sample statistic used to estimate something that's not known inside of the population. And of course, the great example is the sample mean, but there are other things out there like variances and correlation coefficients and all sorts of other things out there that we can estimate, but those are probably the two, the first moment and the second moment of the distribution. So notice that part of the LOS, describe desirable properties of an estimator. All right, so we need to be unbiased. All right, so the point estimator, and the reading uses the notation Greek letter beta, so beta sub I, and notice it has a little squiggly thing on top of it, and that's known as a hat. So we say beta hat is an unbiased estimator of the true population parameter, and that's just a regular beta sub I. So in order to prove this from a statistical standpoint, we just put an expectations operator around the beta hat and say the expected value of that sample is equal to the true population value. All right, so think about this. So we have a mean. We don't know what that true population mean is, but we have samples. All right, and so we take an expected value of that sample mean, and if we expect it to be equal to, on average, right? An expected value is an average. We expect it to be equal to the true population statistic. The population parameter. On average. Now, what that means from kind of a practical, maybe even a tactical standpoint is, let's go back to my dividend yield examples. What did I say that population was? Let's suppose it's 5%, whether or not we know it, but here we don't know it. But think of it this way, that let's suppose that none of our estimates in the samples are exactly 5%. Some are above and some are below. Think of this to be unbiased. The sum above and the sum below, they have to cancel each other out. So that's what the last arrow point down there. This difference should be 0 if an estimator is unbiased. And I remember my econometrics professor in graduate school had this guy for a couple of classes. He emphasized the unbiased nature of an estimator as being super important, but it was met with equal importance by this idea of efficiency. And so if we have two of these, unbiased estimators, then what we want to do is we want to pick the one that has the smaller of the two variances. And then consistency, this is also important, but think of it this way, that as we increase our sample size, so we go from 30 to 50 to 80 to 100 to 1,000, whatever that is, the probability that our estimate approaches the exact true value of the population, that has to be 100%. All right, so let's go ahead and swing to confidence intervals. And to understand a confidence interval, we need to introduce a new term. So a point estimator, a sample statistic used to estimate an unknown population parameter. And this is just another name for the sample mean. It's going to be a point estimator. So you have all this data and you just figure it out, put your finger right in the middle somewhere. All right, there's my point. I'm pointing it. And forgive me, I don't mean to point at you guys as I'm doing this. My mother never always taught me, don't ever point at someone. So I didn't mean to do that, but I was pointing at the data set. So what are we doing with the confidence interval? We know that when we come up with a mean, we know that's an estimate, and we're going to make that estimate with error. So we need to figure out, is our error, is it this big, is it this big, or is it this big? And one way we can do this is by constructing a confidence interval. So to construct a confidence interval, we're going to go ahead and start with the mean. So we call that the point estimator, and then we're going to add and subtract from that. And you'll see that here in just a second. But what we need to know is we need to know about precision. So we're going to have a reliability factor times that standard error that we talked about just a few moments ago. And that reliability factor is going to depend on the level of confidence, all right, confidence interval, the level of confidence that the researcher wants to illustrate. For example, I think I've used this in a previous recording. Whenever I can't remember someone's name, you have all these people in your life and you forget some of these people's names. I always will ask a friend, I'll say, hey, you see that dude over there? What's his name? And so I know it, right? And so the person, my friend will say, oh, that's Todd over there. And I'll immediately say, what's your percentile on that? And they'll say, 50%. If they say 50%, I'm not going to go say, hey, Todd, how are you doing? But if my buddy says 100%, well, then I'm going to go say, hey, Todd, how are you doing? With confidence. All right, so what is the confidence? And so in statistics, we like 90% confidence, but we love 95% confidence. And sometimes we even like 99% confidence. So there's the table right there. 10%, 5%, and 1%, those are called levels of significance, and they correspond to degrees of confidence. What did I just say? 90, 95, and 99. And remember in the previous recording, I showed you how to look at a z-table, and so there are the corresponding z-values for the level of significance and the degree of confidence. So what we want to say is something like, all right, let's go back to my dividend yield. What was that population mean? That population mean was 5%. What was the sample mean? I'm not sure if I gave you a sample mean. Suppose the sample mean was 4.5%. So what we want to be able to say is with 95% confidence, we want our sample to fall within that range. So what is that confidence level? Maybe it'll be between let's say 4% and 6%. We're 95% confident that interval will contain our estimate. That it'll contain our population. So look at our population mean. So look in that first block point. 95% of the intervals would contain the true parameter, which means just 5% would not contain it. All right, so there's our confidence interval equation, right? Point estimate plus or minus a reliability factor times the standard error. So what do we call that? That's our precision. How precise do we want to be? And notice it depends on a couple of factors. It depends on the standard error. So if we have a huge standard error, then the confidence interval is going to be super wide. And so imagine if we say, hey Jim, I'm 95% confident that the true dividend yield of the population of those 6,000 stocks on the two exchanges is between 0% and 40%. Oh my gosh, that does us almost no good, right? So our sampling process has to be efficient and consistent and unbiased, all those things that we just talked about, because what do we want to do? We want to find this where, remember I've said this to you multiple times in other recordings, what we're trying to do is squeeze. We're squeezing down so we have the lowest possible standard deviation. And we do that based on our statistical knowledge here in quantitative methods, and we're going to apply that to lots and lots of stuff in level 2 and level 3. All right, so there's a good old formula there, confidence interval for the mean, right? And look at scenario 1. This is with a known variance. So all we're going to do is take our mean, which is x, and plus or minus, and there's our z value, and we're going to get that from the bottom right column in that table. And we're cutting it in half because we're cutting the alpha in half because it's two-tailed, right? We're going plus and minus, so there's a tail up and there's a tail down, but maybe it's better if you look tail left and tail right. And we're going to multiply it by the known population standard deviation, right? There's that sigma divided by the square root of n. So the key here is reading the question stem. If somewhere in the question stem they say, hey, the variance is known to be 20%, well, there you go. But how about if the variance is unknown? So back here, if the variance is known, just think about it this way, you're going to use z. If the variance is unknown, then you have to go back to the student's t-distribution. And we talked about the t-distribution in a previous recording. Notice with the t-distribution, we really care about n. So that's what we're doing down the left-hand column there. Remember, degrees of freedom, and degrees of freedom for a t-test in this case is going to be n minus 1 degrees of freedom. I know I've done this before, but let me go ahead and do this just quickly again, just to make sure you understand degrees of freedom. If you were in my class and you took 2 tests, and you made, you averaged 80% on those 2 tests. You knew that you made a 90 on the first test, but you forgot what you made on the second test. Well, knowing the mean, which was 80%, right? Knowing the first score, 90, well, you can back in. You can figure out that you had to have made a 70 on the second test to be able to have a mean of 80%. That's degrees of freedom, n minus 1. So if you took 100 tests of mine and you knew the mean was 80%, you'd have to know 99 of those scores so that you can get back into that last one. That's what degrees of freedom really means. And so over on the right hand, each of those columns are different levels of confidence, and those are the corresponding t values. So you probably have to read at least a partial table on the exam. Keeping in mind, let me tell you what I said to you in the last recording. Remember that as n gets larger, the t distribution becomes a z distribution, normal distribution. And so if you have an unknown variance and your sample size is 1 million, you could probably use the z table. All right, how about scenario 3? The population mean when the variance is unknown and the sample size is large enough. This is what I just described. We're going to go ahead and throw that central limit theorem at us, and we can use the z. All right, how about a couple of general comments here? Larger samples are preferred to smaller sample ones because, well, you probably didn't even need to read this reading, right? Larger samples are preferred just because of regular old common sense. But the confidence intervals are narrower, so that's important. And look at that second one. This is probably even more important. This is why we bolded it. Standard error is smaller when the sample size increases. Now, of course, I don't want you just to go ahead and think that, oh, we want tons and tons of observations in every one of our samples because A, it costs money to collect this extra data. But then look at that first one underneath the orange block. However, right, with large sample sizes, it's possible that old data gets mixed in with new data, and that it might not be relevant, it might not be reliable, and it may violate all of those kinds of assumptions that we made about consistency, et cetera, et cetera. So let's be careful, marginal cost, marginal benefit, to decide what is the optimal sample size. Let's move on to this idea of resampling. So what have we done so far? We've taken our population of 6,000 US dividend yields, and we've drawn samples from them. Maybe we did some clustering. Maybe we did some kind of simple sampling. Maybe we did stratums. Maybe we did some other things. But then we get this idea of, I wonder if there's something else that we can do in order to improve efficiency. Because remember, what we want to do is we want to be able to make a conclusion regarding the sample as it applies to the population. So bootstrapping and jackknifing are attempts to try to help us make and draw better conclusions. All right, so notice what we have right above the big old bootstrapping one. Resampling refers to repeatedly drawing samples from the original observed data sample. All right, so we can do this in one of two ways. We can do it through the bootstrapping. And so look at the illustration there going down the original data set, right? So there it is. And maybe we've divided that into different kind of groups, or maybe not. Maybe those are just different samples and those are different means or different, any kind of another statistic. So what we do in the bootstrap is that we go and draw random samples repeatedly, and it's probably a lot easier to do this with some type of a computer algorithm. And so what this allows us to do is it allows us to take, right, and continue to take. And so all of a sudden we have 1,000 copies of each observation, which then over in the green area, that might be more efficient. It might be more representative of the entire population. So notice that second arrow point. The number of repeated samples to be drawn are determined by the researcher. Now, what we can also do is we can jackknife, we can sample, we can withdraw data without replacement. So here, let's go back here. We're just like drawing and drawing and drawing. So we're resampling repeatedly. Here, we're doing this without replacement. And so we need n repeated samples that match the sample size in a jackknife method. And so there we have it. It can be used to reduce the bias of the estimator, to estimate the standard error and the confidence interval of an estimator. Now remember when we had that slide about using our judgments. So when we have judgments, then we're probably going to be subject to some kind of a bias. I mean, I'm guilty of a bias just like anybody. When I flick on the red zone on Sunday afternoons to watch NFL, if I see a Notre Dame football player playing, I root for that team. So I'm biased. Of course I'm biased. Now, that really doesn't affect anybody else in my life, and it doesn't affect the outcome of a football game, and it's really not that big of a deal. But if we have biases in sampling, they're going to dramatically, at least have the potential of dramatically impact our conclusions based on the population. And in fact, they can be so dramatic that we can make the wrong conclusion. Data snooping bias. You probably don't even need to read anything about this to understand what this means. And let me assure you that our professors in graduate school, when my buddies and I were writing our dissertations, we're collecting tons and tons of data. And our professors said, look, whatever you collect, that's what you get. I don't want you going in and saying, oh, here's an outlier, let's throw that out. Here's something that I don't like, let's throw that out. All right, so let me read this to you. Analyzing a large amount of historical data to discover trends, and then data mining, analyze data, statistically irrelevance, all those kinds of good things. Sample selection bias. This is prevalent in lots and lots of studies out there. You will read this when you get to the reading on alternative investments when it comes to hedge funds. There's sample selection bias in some hedge fund studies. Exclude a section of the population. This erodes the idea of randomness, right? What did we say earlier? That the samples, they must be randomly selected. But if you're specifically excluding a section of the population, well then, your sampling is not going to be representative. Survivorship bias. This goes back to hedge funds and mutual funds as well. And there's the example. Hedge funds over a 10-year period would exclude all hedge funds that closed during that period. Backfill bias. Successful funds report their past performance to a database. Of course, successful fund managers are going to say, yeah, look at me, I did a great job. But if I stink, if I have Jim's mutual fund and I stink, there's no way I'm sending that information over there so that everybody knows that I stink. Look ahead bias. This is an interesting one because what are we taught to do as good financial analysts? We're taught to process all this information that we get from financial statements, that we get from reading the Wall Street Journal, from listening to the chairman of the Fed. And what we can expect is we can expect something like, hey, you know what? Next week there's a Fed meeting, and I believe that the Fed is going to announce this and this and this. And I'm pretty sure they're going to do it at 10 o'clock in the morning. And so therefore, I'm going to anticipate and I'm going to look ahead, et cetera, et cetera. But it also includes most companies taking, a long time, let's say 2 or 3 months to release those results. And so there's some kind of a bias in there. Time period bias. Our professors used to tell us about this all the time. Whenever we had assignments inside of a class, like our econometrics class, we would go out and collect data for, let's say, a year. And we'd present the data and our professor would say, all right, that sounds good, but a year, what's cool about this year? Nothing. Does that represent 3 years or 5 years? And so there's a seasonality issue here with time period bias as well. So look for time period bias when we do cyclicality and seasonality at some time in future readings. And that takes us through all of our learning outcome statements. Boy, I love to give students and candidates an idea of what's more important, but boy, I'm having a tough one here with this reading. I think all of these are important.